first talk is on quantum, and we have Raoul, who will be presenting the subject to us. So Raoul is Innovation Manager at Airbus, and he has a whole list of UK institutions that he studied at. So Raoul holds a PhD in wireless communications from University College London, an MSci in communications and signal processing from Imperial College London. He also has a diplôme d'ingénieur from NCA in Paris, and then prior to that, he was a postdoctoral researcher at the Experimental Quantum Information Lab at the University of Leeds in the UK. And you were working on a free space quantum communications project at the Quantum Communications Hub funded by the Royal Academy of Engineering. So Raoul has a real background in this subject. He's a real expert.
So thank you for being here this evening. And thank you for the British Council for giving us the opportunity to organize this Tech Made Simple. So with my colleague Daphne here, we've been organizing these talks. So we thought, what's the best topic to start with, right? Something that can be made easy for everybody to follow. And the topic would be quantum, right? So that's the easiest topic that you can share with people. I don't know if there are any physicists in the room. I might be saying some things that are slightly, not the most correct in terms of the physics purist, but the goal here is to help people understand the technology, and then what can we do with it, right? So the title, The Quantum Revolution, Myth or Reality. What I've kind of decided to do here is to go through history and then lead you to the kind of modern understanding of quantum physics and what we can do with it. And we're going to try and have something a bit more interactive. So the first question is myth or reality? All right, so I guess both is the winner here for now. All right, we have 38 people, 38% I think it's reality, and then, what is quantum? This is actually the target audience, right, for tonight. What is quantum? All right, so let's start. A quick outline. So before we talk about the quantum revolution, the idea is to look at, okay, what was before the revolution and before the whole quantum started. Then we're going through the first quantum revolution and the second quantum revolution and the discussion. So what the definitions are going to come during the presentation. So what was before the revolution? Before the revolution was certainty, right? So people thought, they knew how the world worked. You have some physicists that would say things like this. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement, right? So the thinking at the time was, we know how the physics works. We know how to explain the movement of planets, charged particles, and we just need to know how to. We can just measure, if we measure precisely enough the position of particles and their charge, we can predict their movement, right? So you could, from the position of planets at a certain instant, you can know where they're going to be in the future. So this meant that we could know everything from certainty, with certainty, just by knowing the position of things at a precise time, right? So we had Newton's for motion, Maxwell's equations for electromagnetism, and then to understand how charged particles moved, we had Lorentz equations, right? So with this, you could actually do most of physics, most of known physics. So this is prior to 1900. And the applications, the steam engine, electricity, right? So we could electrify cities. This is in Paris, Paris Exposition, 1878. So we could build electric vehicles. This is actually a surprising one from 1895. Electric vehicles, this is in the UK. And airplanes, right? So with that level of physics, we could already build all this. We understood how this worked, and most of what we do today actually also still works according to these laws. You don't need to know a lot more than that. You can put things in orbit using the Newton's laws of gravity. So now comes the first quantum revolution, which is about quantization. Right? So it's the understanding that things actually comes in packets, but we're going to see that. I put another quote here, which is, so just the idea is that when there's a new idea that comes in science, it's not necessarily because the ideas are convincing that people will adopt them. It's because eventually the people that were believing the old ideas would die, and then the new generation would actually just be raised with the new ideas and adopt these. And then this is actually what started the quantum revolution, the first quantum revolution. So we have Max Planck, a German physicist, that he wanted to actually understand how, let's say, how to optimize a light bulb, right? So you have a light bulb, it's sending light, and you want to optimize the light bulb so that most of the light that is coming out of the light bulb is emitted within the visual part of the spectrum, right? At that time, we didn't know how to do it. We had some theories that would explain a little bit at some part of the spectrum how the light was emitted, but when you went to shorter and shorter wavelength of light, so like ultraviolet, the theory blew up. So we didn't know how to do it. And then Max Planck came up with the idea that energy, if we actually accept that energy can be absorbed and emitted as small packets, then you could explain how that radiation was being transmitted, how the energy of a body that's heated is radiated. And then Einstein actually used that idea and applied it to something else, right? So there was this phenomenon that people didn't understand, that when you shine light on some metals, the metal will produce electricity. And the relationship between the intensity of the light, the frequency of the light, and the electricity being transmitted wasn't necessarily clear. So Einstein managed to explain it using the fact that light was quantized, right? So this is another way in which things are quantized. Light, if prior to that, was thought to be a wave, right? So there's some kind of wave that was traveling in space. And at that point in time, it was actually thought, oh, maybe this is a particle as well, right? So if it's a particle being absorbed one chunk at a time, then an electron could be released as well, one chunk at a time. That's the broad idea. Then something else came up. So Niels Bohr, another physicist, decided, what if we quantized the atom as well, right? You have an atom, we didn't know exactly what the structure of an atom was, so he postulated the idea that a hydrogen atom, the electrons, were allowed to move on some kind of different levels around the nucleus of the atom. And that enabled Niels Bohr to understand some kind of rays that would appear in the spectrum of elements that contained hydrogen, right? So this is, again, another instance where we had quantization that appeared. And then one last thing before we go to the second quantum revolution is that matter actually also behaved as a wave, right? So before we thought, oh, light was a wave, but then we realized, oh, light behaved like a particle. Now we have particles, things that we thought to be particles, that also behave like waves, right? And because they behave like waves, you can have this kind of interference pattern that are created when you run some experiments with them, right? So this is an actual result of an experiment with electrons that are interfering with themselves to create this pattern, right? So you have the individual electrons hitting the screen, and you have like an interference pattern that appears there. And I have another question here for you. In 1916, Einstein theorized the laser. How long did it take to build the first one? So After his work on the quantization of light, Einstein theorized that you could, putting I guess you could put the light in a state that would, how to explain it? Well, essentially, you could build a laser out of light and out of understanding how the atom works, right? So he theorized this in 1916, and then it took 44 years before the first laser was built. So this is actually to just show that the applications that come out of these theoretical developments can actually take time to materialize, right? Some of them actually are quite short, some take some time. So the first one that I want to show here is the first electron microscope. The first electron microscope was built in 1933. So if you remember what I said before, so we had de Broglie that showed that, who theorized that matter also behaved like a wave. And because it behaves like waves, you could use it to do diffraction. The same things that you do with light, you could do with matter. So building a microscope that uses electrons is actually a direct consequence of that. And this didn't take long, as you can see. The transistor, right, this is something that powered the computing revolution, came out of the development of the first quantum revolution. The pin photodiode, so it's a detector of light, was invented in 1950, and this is what has been used to, well, you could find it in the CD players, for those who remember what they are. You know, so you could use it to read, so you would shine a light on the CD, and then the photodiode would read the instructions on the CD, and that's how you would get your movie or your music. And so 1960, the first laser is invented. So from 1916 to 1960, so that's 44 years. And actually, there's a caveat. There was a different type of laser that was invented a bit before, but this is where the first laser was invented, and the transformational power of the laser is, the amount of applications that rely on that is tremendous. So, we all see the barcode readers, but also building integrated circuits rely heavily on being able to manufacture lasers. So the entire information age actually relies upon these discoveries of the first quantum revolution. So just a quick recap. So the things that were thought to be waves also behave like particles. The things that we thought to be particles behave like waves. Energy is exchanged in packets, so that was a new idea. It wasn't necessarily accepted from the beginning, but as things go on, people realize that actually the same idea comes up everywhere, so there might be some physics to it. Light is also absorbed and emitted as packets. And also these simple realizations, as I said before, underpin the whole information age, right? Obviously, there is a lot more to it as well, Shannon's theory of information and all that, but if we look at physics purely, it underpinned the developments that came after. And so we come to the second quantum revolution, about 1925. So we throw certainty out the window, and here comes uncertainty, right? So uncertainty in many ways. I like this quote from Heisenberg. So only a few know how much one must know to know how little one knows, right? So in a sense, it also goes back to where we started, right? Where we thought we knew how the world worked. We already had figured out all the basics of physics, but actually we didn't, right? And it took us 25 years from then to realize actually the world works completely differently from what we thought. So let's see a few things. So something that I didn't mention is, so with the first quantum revolution, in a sense, it still feels natural, right? So you can still have an intuition of what's going on, right? So you have, particles that fall, a cannonball that moves. You kind of understand this. Then you have so waves that behave a bit like packets. You think, okay, you know what? If you just take packets of things, and then what's actually the big deal? Right? You have things that behave like chunks. We can move them around. It's not. It's transformational, but intuitively you could still kind of wrap your mind around it. When we start thinking about matter behaving like waves, it gets a bit more tricky. And so we get here. So the previous part, if you notice, I had images before. Now it's only equations. And I think something actually shifted there. The experimentalist got replaced by a theorist in physics, in a sense. So things become like purely, really heavily mathematical and it actually represents the fact that the understanding at that level is like it transcends our intuition. It's difficult to actually wrap our minds around it. So we devise these equations that actually describe how the world works, but we don't have the intuition around it anymore. But so the first equation here is one that's really well known, the Schrödinger equation. Everybody's probably heard of the cat that is both dead and alive. So this one came out of directly the work of de Broglie that was thinking that, matter behaves like waves. So if it behaves like a wave, there must be a wave equation, some kind of equation that works like, that describes waves, that is also describing how matter behaves. So this is one key building block of that second quantum revolution. We have the uncertainty principle, right? So that is saying, you can't know certain parameters of certain properties of a system, some pairs of properties. You can't know them with infinite precision, right? So you have a limitation on understanding this. We have another equation here, Dirac equation. Again, it's the point is not to understand this, but to see something actually shifted, right? We can actually kind of build a feeling of what's going on to, well, we're just given some equations that describe how the world actually works, but and these equations are really precise in predicting what's happening, but it's difficult to actually know what's going on. So just for description, the Dirac equation, in a sense, gives you the effects of, well, it's kind of Schrödinger's equation when you have particles that move really fast, right, close to the speed of light. So this was like another building block of physics. And in the 1930s, we actually have another physicist, Dirac, that kind of formalized the whole theory of quantum physics, giving different postulates that would explain how the whole theory works, so you could use them to predict the behavior of quantum particles to an extremely good accuracy, right? But again, it's a whole mathematical framework that gives you that, but the intuition is difficult to build around it. What effects can we see with it, right? So something that you've probably seen that's called, or heard of, is called tunneling. So you have, let's say, some charged particle, let's say an electron that's moving in an electric field. There's a barrier that it cannot normally cross, but then somehow it's able to cross it. The reason is because of the wavy nature of it, right? So it gets to the barrier and then it thinks, oh, well, there is a part of its wave function that is on the other side and the other part that's going back. So it gives you some kind of probability that it's crossed it. That's one of the effects. Another effect is you could have particles that are connected over long distances. So let's say you have, you represent the particles by a coin, you put them together in some kind of ways, they get entangled. Then when you separate them over long distances, they remain connected in some kind of interesting way. So the measurement that you do on one will affect the other one, regardless of how far they are in the universe. So these are two key properties of quantum physics that we're going to see how they are being used in applications later. Just a quick recap again this time. So we have a superposition, right? So because things are behaving like waves, they could be, a bit like you have waves in the pond. You have two waves that interact. They can superimpose and then have some kind of interference. We have entanglement that I just mentioned. So particles can be far apart, but they still have some kind of connection. Tunneling that I just showed. So you have particles that when they encounter a barrier, they can go across the barrier even though they're not supposed. Classically, they wouldn't be supposed to go across. And then there's something which is the measurement, in the sense of when you measure these quantum phenomena, you find something, right, like a classical answer, but you lose the quantum properties. And something that's actually really important in this second revolution is that we actually have been getting better and better at understanding how these handling this quantum state, right? So measuring the position of an electron, measuring these interference patterns. So this is something that we've been getting really good at. And that helped us to build really precise sensors. And so, for example, this is a LIGO in Livingston in the US. It's a laser interferometer to measure gravitational waves. And we actually measured the first one in 2015, I think. And in order to do this, we actually have to be able to measure things really precisely, right? So I have one other question for you here, which is, what's the magnitude of change this detector can measure over its 4-kilometer mirror spacing? So the detector that you saw, the arms that made a 90-degree angle, they have a mirror at both ends, so they're sending a laser beam that will bounce between the mirrors and interfere. And it's actually, the purpose of it is to measure the change that will happen in the length of these different arms when the gravitational wave goes through. In order to measure that, we need to have really, really good sensors. So this is the precision that we can have. So 1/1000th of the size of a proton, right? So a proton in size is 10 to the minus 15 meters. I don't even think we can represent how small that is in our minds. And this detector is able to measure things that are 1/1000th of the size of a proton. So in terms of accuracy, it's just mind-blowing. This is something that we can build using quantum mechanics. Another thing that we can build using quantum mechanics, using the tunneling effect, is microscopes, which can also move atoms. So here's a video by IBM that was released 11, 12 years ago, where they decided to make the smallest movie on record, right? So that was a world record. And they made a movie called A Boy and Its Atom. And so what you can see there, the little dots are actually atoms, and I'll let you see part of the video. So in order to make this video, what they did is they used a tunneling microscope to move individual atoms, uh, one row at a time to make a few frames that they could actually put together after to make a video. So this is an impressive, I'm just going to stop it. This is something else that, for me, it's impressive to see that we could move individual atoms around with the precision necessary to make a video like this, right? And obviously the impacts in chemistry are tremendous, right? Being able to see individual molecules, their structure, moving atoms around like this. So this again is another thing that we couldn't have done without the ideas of the second quantum revolution. Something that actually is closer to what I worked on when I was doing physics is quantum key distribution. So in order to send important messages on the internet, we need to encrypt them. And today we're using security protocols that are based on mathematics. Some mathematical problems that we know to be really hard to crack. This is an alternative, is using quantum physics, especially the way that when you measure a quantum system, the measurement will disturb the state of the system, right? So it's the idea of the Schrodinger's cat in the box. When you open it, it's definitely dead or alive, but you don't know it before you open it. But once you open it, the state is defined. So we do it here with not cats, but photons. And we could devise protocols that will allow us to send messages and detect when somebody has been eavesdropping, right? So if you send if you want to send a secure key, a key that we will use to secure your messages afterwards, then you use this protocol, and by using quantum mechanics, you'll know whether the key is actually secure or not, right? If it's not secure, you throw it away and you start again. If it is secure, then you can use it to encrypt your messages. So this is another application of quantum mechanics. The one that you've probably heard about is quantum computing, right? So quantum computing is based on quantum bits. So quantum bits are, the quantum systems that have two different states. Let's say we call it zeros and ones, like the normal bits. But because they are quantum, these states could be superposed, right? So they could be in some kind of mixture of zeros and ones. So this is what I'm showing here. So it's a quantum bit in a superposition. It's got a bit of red and a bit of green inside it. But again, when you measure it, it's going to be either red or green, right? But before you measure it, it's going to be in a superposition of the two states. You could have two of these independent quantum bits, and with these two independent quantum bits, you could actually do more than what you would do with two classical bits, right? But there is an additional property that we saw before called entanglement. So you could also make these two quantum bits connected with this kind of interesting quantum property that means that they connected even from at a distance. And when they connected, they can actually also process more information, right? So when building a quantum computer, it's important to have that superposition and also the entanglement, right? So the actual hard challenges are to maintain the entanglement that gives you the full capacity of a quantum computer, and maintain it over a lot more than just two quantum bits. So you've probably heard of this in the news recently. So Google said they built a 105 qubit computer, right? So it was said to be, a major milestone. You could solve problems with this much faster than you could with classical computer. And then you can also see right here the CEO of NVIDIA that's saying, well, actually, that's really, it's interesting, but you know what? Wake me up in 20 years, because he doesn't think that there is any threat of quantum computers before then, right? So this is the tension here. So we have new development in quantum computing, but we're also not sure, where along the line of development it is, right? And then I want to kind of think back to the laser another example, where in 1916 Einstein kind of theorized the laser, and in 1960 it was actually built. So here we have the quantum computer, right, that we also expecting to be built at some point. We have the theory that's underpinning it, but we don't know when it's going to happen. It could happen actually quite quick, as it happened with the electron microscope, or it could take longer. So what actually was the exciting thing about the Google quantum computer is that they managed to reduce errors, right? So what's happening is, as I said, when you're building these quantum computers, you have the quantum bits. They are entangled, but sometimes they will interact with the environment, right? So there might be a photon going around, or there could be anything else that will perturbate your system. And you're trying to reduce the errors that are in the quantum computer. And to do that, you have some sort of algorithms that will correct these errors. And what they've actually showed is that they could correct. You need to add less quantum bits than the amount of error that is added once you've done the correction. So because prior to that, the more you added, the more errors you had, and then the more you needed to add in order to correct the errors that you've added, right? So it's a little bit of a loop here. So they show that you can actually scale much better than that. So it's actually a big advancement because it shows practical quantum computers are possible, right? So you could you could reduce errors much faster than the number of qubits that you're adding. And the second thing that they showed is that they managed to solve a problem 10 to the 25 times faster than the fastest supercomputer, right? So this part here is actually not it's really interesting, but then you have to look at this graph that they showed, which is you have commercial relevance on the x-axis here, and then on the y-axis you have the difficulty of the problem. So the problem that they solved is the problem of random circuit sampling. Don't need to know what that is. But when you look at the commercial relevance, it's far to the left, right? And on the difficulty, all the way to the top. So that means it's a kind of useless problem, but we can solve it really fast with a quantum computer compared to what we would be able to do with a classical computer, right? However, it's it's still an achievement because it's a problem that we currently cannot solve fast enough with a classical computer. So, and this is not the only type of problem that we think we can solve much faster with a quantum computer than a classical. So this is the part that is of interest to us, things that are beyond classical, so more faster on a quantum computer than on a classical, but also commercially relevant. For example, factoring large numbers. And so, for example, if you're able to factor large numbers, you can break security codes on the internet. So you can read people's email, you can access their bank accounts, and so on. So these are the type of problems that will fit in here, and that hopefully one day quantum computers will be able to do. I don't know if I should say hopefully, because I don't want my bank accounts to be broken into. But they are not the only problems. There are problems in chemistry that will be able to solve much faster as well. We may be able to do it on a classical computer, but it would be much faster on the quantum computer. So chemistry, quantum chemistry. There are some problems in machine learning as well that could be solved much faster with a quantum computer. And on the Google's roadmap to achieving, full large-scale quantum computer, we are about milestone 2, right? So the first thing was beyond classical, so showing that we could solve a problem with a quantum computer much faster than we could on a classical computer. Then the second one was to show that quantum error correction that I talked about earlier, that you could correct more errors than you were adding, in a sense. And the next milestones would be building a long-lived logical qubit. So one of the issues today is the entanglement that you have, you lose it quite fast. So when you lose it, you lose the ability to do quantum computation. So one of the challenges is to be able to maintain that for a longer period of time, and that will allow you to do calculations on much longer time frame, and also more complex calculations. Creating a logical gate. Let's say I'm not sure how to go to the analogy here. On classical computers, you have gates when you put zeros and ones, and they give you an answer on the other end. And on quantum machines, you have the same processes. You have your quantum entanglement or superposition of zeros and ones. You put them through a quantum gates, and they give you an answer on the other side. And these gates also need to be implemented without errors. And so this is the next milestone that they have. And then you get to the engineering scale-up. So once you've solved all these problems, you need to think about how to put them all together and on a bigger scale in order to actually tackle the problems that you want to tackle. So the roadmap is there. One interesting thing is they've put the date there for 2023, and that stops because as it's a research topic, you don't know when it's going to happen. So it could take 5 years, 10 years, 15 years. We don't know. So we just have to live with the quantum threat above our heads. So maybe tomorrow somebody can hack into your bank account with it. You don't know, right? We're fairly confident that it's not happening today, or it hasn't happened today. But the general trend is to take that into consideration and already start updating systems that could be vulnerable to quantum machines in the future, especially if you work on systems that will collect data that will have a long lifetime, right? So you have data that will be available or still valid in 20 years, then you need to think about quantum computing today, because somebody could record that data today and then decrypt it in the future with a quantum computer. This is a Google search that I did. And so I wanted to know the largest prime number that was factored with the quantum computer. And it's 21, 3 times 7. I'm already as good as a quantum computer. And this was actually done in 2012. So, well, it's been 13 years, and still the biggest number, right? So it's interesting to see the advances and what you actually can do with it. The rest of the response there is actually also interesting. It hints at, so there's other type of quantum, so there's multiple types of quantum computers, and with some of the type of quantum computers, you could already factor some larger numbers. However, yet it hasn't been able to do anything much faster than a classical computer. So we're reaching the end here, and I've gone way over the time. So the conclusion, myth or reality? And I'll leave you to it. And we can go to the Q&A. Thank you.
Thank you very much for this very interesting and clear presentation. You mentioned the Shannon information and communication theory. Is there a quantum version of this information and communication theory?
Yes, there is actually. So you have quantum information theory. And what it adds is So these entanglements, so right, you have these correlations that cannot be explained classically. And with these correlations, you can actually send or process information much faster, or you could send more information that you would with a classical bit, for example. So there are, you might have heard of teleportation, right? So you could teleport a quantum state. So in order to explain how the transfer of information in that context, you would need to have a quantum theory of information. And so that theory actually exists. There's a great book on it by Nielsen Schwang, and it derives the whole theory and the equivalent of Shannon's theory.
Does that mean that the information goes faster than light?
No, the information actually doesn't travel faster than light. So, there's always a bit of a caveat there. So you have your, let's say you have your two entangled states, one on the planet Earth, the other one on Mars. In order to know the state, when you measure a state here, in order to know what the state of the particle on Mars is, you would need to have the information sent to you, right? So this is the caveat there, so you wouldn't be able to send information faster.
I wonder if Airbus is interested in quantum communication, and if so, in which application fields?
Oh, Airbus is working on a few projects. So there is a European project called Euro QCI, led by Airbus, and where they are working on a quantum network, a European quantum network. So you have to actually know that in the world now, there's quite a few institutions working on this. In the UK, there is a quantum network led by the teams working on it were part of the Quantum Hub. You have the University of Oxford working on it. You have BT working on it. Toshiba as well working on that. In Europe, so there is also a consortium with Airbus part of it that's working on these quantum networks, right? So the idea is to connect a few different sites using really optical fibers and to exchange information using quantum cryptography.